got the record. So welcome everybody to lecture 2 of the spring 2025 Intro to Space Navigation. So today it's going to be the first full math day, as opposed to Monday was kind of just introductions and then a quick, math exercise. It's going to be all handwritten notes in OneNote by me, and I have to warn you that my handwriting is not great to begin with on paper, and then on the pen tablet it's worse. And I remember last semester when we taught this, like over the course of the semester, I got slowly better at the handwriting, but right now it's going to be rough. So bear with me. It's going to be a bit of a learning curve for everyone. So today, I'm going to go ahead and share my screen. I don't know if you can hear it in the background. There's like a rain, wind, thunderstorm going on right outside my apartment. So I don't know if the like howling wind from Edgar Allan Poe comes through the microphone, or hopefully that gets canceled out. But if that's annoying, let me know and I'll see what I can do about it. I'm going to go ahead and share my screen. There we go. So lecture 2 is going to be about, there we go. It's going to be about reference frames and epochs. So in a lot of these lectures, I like to start with kind of a thought experiment, and typically that involves picking on somebody and asking them a bunch of questions that are often fundamentally unanswerable, just as like a food for thought thing. But the downside is you might look a little dumb when you're being questioned, but rest assured that it's all part of the process, and we know that you're not dumb because you wouldn't have made it in this class if you weren't. Do I have a brave volunteer to answer some tough questions about space to kind of get our conversation primed today?
I can go for it.
All right, here we go. So let's say we have a spacecraft, and I'm going to draw the spacecraft. You'll see a lot of this as like a little cube with solar panels coming off the side. Okay, so this is a navigation course, right? So navigation is determining where the spacecraft is. Okay, where is that spacecraft?
Where is it relative to what?
Ah, that was exactly what I was looking for. Relative to what? Okay, so now let's say hypothetically, that was the right answer, by the way. Let's say that we have the Earth right here next to it. So here's the Earth. Here's some continents. Okay. Great. Now, where's the spacecraft?
Again, relative to the center or the surface of the Earth?
Yep, it's still getting, okay, fantastic. So let's say relative to the center of the Earth. So let's say that I've got a vector starting at the center of the Earth and going out to the spacecraft. Okay, great. We're still not there yet. What are we still missing?
I'm not too sure. I think this one vector should be enough, but
This one vector. Okay, so what is that vector? Like if we wanted to sit down and write it out.
I mean, it would be the distance and the angle relative to like latitude and longitude, probably.
Ah, there it is. So implicit in your answer is that we need some sort of direction system. Yep. So that was also the right answer. Very good. I was usually people are stumped by these sorts of things. In order to answer this question, we need a reference system. So jumping to latitude and longitude is a Earth-centered, Earth-fixed reference system. We don't necessarily have to use that one, but we need basis vectors to be able to answer questions like where is the spacecraft? And you might have wondered this, if you've got a spacecraft like floating in deep space, first of all, where is it? But like, how do we even begin to answer that question? We need some sort of like global X, Y, and Z directions that are not tied to a planet. Like, do those exist? And the answer is that those absolutely do exist. And so that's what we're going to be discussing today. So thank you, Michael. That was very good job. So you're off the hook. And now I'm just going to write for a little bit. So get your note taking hands all warmed up. So navigation means determining your state from available measurements of your surroundings. I'm just going to say from available measurements. Now, unlike a spacecraft, a state cannot exist in a vacuum. That is a dumb pun. Sorry about that. So a spacecraft, you can throw it out into a vacuum. A state, like state, what do you mean? Like position relative to what? Relative to what was the key words I was looking for there. Position relative to what? Or velocity relative to what? And I guess I should say, when we say state, we typically mean position, velocity, and attitude. Attitude meaning orientation. Okay, great. So let's make this make a little bit more sense. So I like to think in terms of degrees of freedom. You're going to hear me use the phrase degrees of freedom a million times this semester. So on the Earth, how many degrees of freedom are there in a navigation problem? Let's say you're an old-timey nautical navigator sailing the high seas. How many bits of information do you need before you can confidently say you know what you need to know about your vehicle? I would argue that it is 4 degrees of freedom. Does anyone want to? Oh, I see, Peter, you had your hand up. What do we got?
Well, your latitude, your longitude, your speed, and your direction.
Perfect. Direction. How are we going to describe direction in this case?
North, well, relative to magnetic north, most likely.
That's exactly right. Perfect. Good. So on Earth, we have position, which we can think of as latitude and longitude. So there's 2 degrees of freedom. We also have speed, not really velocity. In this case, this would be measured in something like knots or a nautical vessel or miles per hour. Take your pick, right? Knots per hour. And this is 1 degree of freedom. You're either going fast or you're going slow. And then finally, you've got your heading, which is the direction of travel, right? And we could think of this as angle with respect to north. You know what? I can do better than that. Hang on, bear with me. Angle respect to north. And that's marginally better. And that's also 1 degree of freedom. So I would say on the surface of the Earth, it is a 4 DOF problem. You need to know 4 numbers. Okay, so somebody else, what about, I was about to say on space, what about in space? How many degrees of freedom are there for your state? I'll start us off. We've got position. How many degrees of freedom are there in position? Oh, yep, I hear somebody.
Yeah, position is 3 degrees of freedom because you're working in 3-dimensional space now, X, Y, and
Yep.
Z.
And while you're on a roll, what about your velocity?
Velocity, you're gonna have individual components related to each position. So you have an X dot, a Y dot, and a Z dot.
Absolutely. And now finish it up.
Same with the heading. Each angle with respect to X, Y, and Z.
Perfect. I'm going to call this for now. Yep, I'm going to call this roll, pitch, and yaw for now. And we'll talk a lot more about attitude later. But yep, very good. So that's also 3 degrees of freedom. So in space, state estimation is a 9 degree of freedom problem. Okay, so now X, Y, Z, X dot, Y dot, Z dot, roll, pitch, and yaw. Those are all angles with respect to basis vectors. All right, comm check. Can y'all hear me?
Yeah, I can hear you. I can hear you. The screen
Okay.
disappeared.
Yep, the screen will do that. Sorry about that. My headset, I have a Bluetooth headset that I'm talking into, and it just gave the disconnection sound. So stand by. I'm gonna make sure. I don't think it's low on battery, but I'm gonna plug the thing in just to be safe. Apologies for the dead air time here. Okay, I think I got the headset thing fixed. If I have further microphone issues, then I'll just go ahead and have everybody break for about 10 minutes while I go scrounge up a different microphone. But for now, I think we're walking the tightrope. Things seem to be working. Can I just get a quick see the note page again?
Yes.
Nice. Okay, good. Good. Thank you so much. All right, these are the growing pains of I have a new computer from the last time I taught this class, and I knew there were going to be little hiccups here and there. So thanks for putting up with it. So a reference frame requires a reference point and basis directions. So imagine we've got a situation where you've got, let's say, the sun. And whenever I draw the sun, I usually put the little shine lines on it so you know which one we're talking about. And then let's say you've got the Earth orbiting the sun. And then you've got the moon orbiting the Earth. And then maybe you've got a spacecraft orbiting the moon. We could have a sun reference frame. We could have an Earth reference frame. We could have a moon reference frame. We could have a spacecraft reference frame. And those frames all could have different relative orientations to one another. So it's going to be a little bit tricky to bookkeep all of them. And then even within the spacecraft frame, there's the spacecraft body frame, but there might also be an instrument frame, like a camera frame. There's an abundance of frames, and we're going to spend most of the rest of this class dealing with numbers either in some frame or talking about the relationship between frames. So we're going to need to make friends with those really quickly. So before we can even get down to talking about frames, it's not obvious what directions we ought to use when forming a reference frame. So for example, I'm going to use this symbol, backward Z with a line through it. It means there does not exist. So it's just shorthand. There do not exist any fixed points in space, right? Everything is moving with respect to everything else. So how can we ever pick a direction? So instead, what we do, we define a direction as it was at some particular point in time or epoch. So therefore, 3 dots means therefore, a discussion of celestial reference frames requires a discussion of time and timekeeping. Okay, so good pausing point. Questions up to this point, or we're good to start talking about time? All right, I'm gonna keep moving unless somebody pipes up. So the next section is called A Brief History of Time. Also a fun reference. There we go. So the most basic unit of timekeeping, the stuff that would have occurred even to cavemen, is the day. Okay, so really quick, whoever's feeling brave and I haven't heard from yet today, what is a day?
Well,
Uh-oh.
I that we measure a day in 24 hours typically.
Okay, but now that gets tricky because what's an hour?
Like with respect to like the conventional time system, or
Well, that's what I'm asking about. So we're starting from scratch. We're going to talk about the conventional time system. But like if you're, just starting from nothing, what is a day? You could say a day is 24 hours and then okay, well what's an hour? What's a 24th of a day? Something needs to be like rock solid, right? Like, oh, well
like
we know. Yeah.
full rotation of the Earth.
Okay, so now we're onto something. So it's a full rotation of the Earth. Even then we start to run into issues. So first of all, I answered a question that's almost impossible to get right. So I'm sorry. I feel kind of mean where I'm like, hey, quick question. You're wrong, but that is the nature of it. What I'm trying to get across is that it's actually really tough. Like all of our concepts of time make sense to us because we don't ask that many questions. But already scientists argue about what a day is exactly. So you might call it the average duration of time it takes for the Earth to spin on its axis. But then it's like, by that definition, every day is a little bit different in length than every other day. Or you might call it the time from apparent local noon, so highest point of sun in the sky, to the next time of apparent local noon, which is a different definition of a day, by the way, from one rotation of the Earth on its axis. That one also is varying. So you might say it's 24 hours. Well, then what's an hour? And so it ends up getting pretty wibbly wobbly pretty quickly. And so we're going to talk about starting from the day, we eventually reached a point where we needed a nanosecond accurate measure of the length of a day and kind of how we got there. So let's start with seasonal hours. So let's just assume that a day is the length of time from noon to noon. From in terms of cavemen, that's plenty accurate enough. So then the next thing that people came up with was seasonal hours. So seasonal hours are when you divide the sun up time or daytime into 12 equal sections, and then also divide the night into 12 sections. night into 12 sections. But then by definition, seasonal hours are going to have varying length. So that's probably fine if you're an agricultural community. But nowadays, we tend to like the fact that every hour is the same duration as every other hour. So far later in history, equinoctial hours, hope I'm pronouncing that right, equinoctial hours came about, which is divide the day-night cycle into 24 sections, which are constant with respect to time. Or we'll say constant from day to day. How about that? So an hour just is 1/24th of a day. That's why we can say that the day, the sun up part of the day is a certain number of hours, and the sun down part of the day is a different number of hours, because hours are just something that we treat as static, even though the motion of the sun changes with the season. So that's equinoctial hours. That's what we're used to. So from there, that eventually became not precise enough for some people. So what you can do is divide equinoctial hours into 60 degrees of minuteness, minute meaning small. And that is where we get the term minute. Comes from minute. And some people said that's not good enough. I need an even more fine measure of time. You can also divide minutes into 60 second degrees of minuteness. So because it's been divided a second time, those are called seconds. Okay, so at this point in time in history, let's say 1700s, early 1800s, seconds would have been kind of a concept that people have heard of, but they don't really work with on a day-to-day basis. The same way that we maybe have heard of like nanoseconds, but we don't really work with them on a day-to-day basis. It's like that's far too accurate for anything that I do with my life. I don't need that. What really was the driving factor for having very accurate clocks which are synchronized to one another was the railroads. So all of the towns need to agree what time it is, and they need to agree with one another. So railroads forced us to synchronize our watches. All of a sudden, in this case, minutes matter. And with the advent of radar and light-based communications, nanoseconds matter. So what we came up with as a way of solving this nanoseconds matter problem is something called atomic clocks. And so we're going to talk about how to measure nanoseconds with atomic time. Okay. So according to atomic time, well, let's start with this. If we define 1 second as 1/60th of 1/60th of 1/24th of 1 day, that is not good enough for nanosecond applications because days vary in length. So you could also say 1 day equals time from noon to noon is also not good enough. We need something better. So what we do now, the new unit of SI time, so International Standard Time, or sorry, apologies. New unit of time is the SI second, so the International Standard Second. Further, sorry, I am just misreading my notes today. My apologies. The new base unit of time. So we're not starting from days and then whittling our way down. We're going to start from seconds and then work our way back up. It's the SI second, which is designed, or I guess defined, to be measured by atomic clocks. So atomic clocks count cycles of a high frequency electrical signal that is kept in resonance with some atomic transition. So the new definition, some of you might have heard of this before, is the SI seconds is equal to 9,192,631,770 periods of radiation corresponding to the transition between two hyperfine levels of the ground state of the isotope cesium-133. So you might have heard of cesium clocks or cesium seconds. So nowadays, seconds in the kind of global standard are measured as 9,192,631,770 oscillations of cesium-133. And then we work our way back up to our definition of hours and days based on that. So the time system based around this second is International Atomic Time, or TAI. And the acronym is backwards because it's French. So TAI, introduced in January 1972, is the basis for interpolation and prediction of all other time systems. Okay, so also just want to highlight, this is going to be a real word-heavy day today. This class is not like this generally, but we kind of have to start from definitions. The math is going to be much, much more later. There will be times when you miss all the words. But yeah, if your hand is cramping today, my apologies. This is a temporary state. So the next thing I wanted to talk about is sidereal versus solar time. And actually, this goes back to, I forget who spoke earlier, one rotation of the Earth on its axis is different than the time from noon to noon. We're going to get into that in a second here. So the next is sidereal versus solar time. So let's talk about what a day is. So we talked about what an hour is. Days fluctuate in length. Due to perturbations in Earth's rotation. So in this case, when I use the word day, I'm not talking about sun up time, which we know changes with the seasons. I mean, time for Earth to spin on its axis is also not constant. The Earth's spin rate is changing with respect to time. So we could define the solar day as apparent local noon to apparent local noon. And then we can just say that that is 24 hours by definition, which we get into some trickiness right there. But you could also say that the sidereal day, measured by looking at stars, is a 360-degree spin of Earth about its axis. And that's also 24 hours. Just kidding. That is, unknowingly, 23 hours, 56 minutes, and 4 seconds on average. How can that be? So I want to kick that back to y'all. Maybe one of you might have some idea. How can it be that the time from noon to noon and the time it takes Earth to spin once on its axis are not the same? Maybe somebody's familiar with this concept already, or maybe you can take a stab at it. Is that you, Peter?
Yeah, the reason that a sidereal day is longer than a solar day is because as the Earth moves along its orbit, the quote, so to speak, the position under the Earth at which the sun is slightly different. So as it moves along its orbit, it is the time it would take to because the sun will be at a different position the next day noon as it would be. It's kind of,
No,
funnily enough, it's kind of hard to talk about without regards to the while trying to think about the reference frames, but the sun will end up being in a different spot in the sky, so to speak, but against the essentially fixed sphere of stars and such around us. That rotation, that revolution around the sun is not a factor, and that is just the Earth turning 360 degrees. When it's the sun, different position in the sky at the next day's noon, so the time is slightly different.
Yep, I think that's pretty well put. And I think it also comes together a lot when you have a picture. So in this case, we're going to say that the Earth is orbiting this way and then also rotating this way. And so what ends up happening is from this point to this point is one sidereal day. And then from this point to this point is one solar day. So this is sidereal and this is solar. So yeah, the sun, of course, the sun isn't moving with respect to a sun-centered reference system, but you can think of it this way. The Earth is in a different spot in its orbit. And so the time it takes to spin once on its axis, this is an exaggerated drawing, of course, it hasn't actually craned around to be pointing at the sun again. So that extra roughly 4 minutes represents the amount of time that it takes the Earth to account for its own motion, basically. So the apparent noon takes slightly longer to happen than one spin about its axis. And then if the Earth's rotation was the other way, or if the orbit was the other way, it would be slightly longer, slightly shorter. You get the idea. But a sidereal day is measured with respect to stars, and the solar day is measured with respect to sun. So hopefully that makes sense, and hopefully the picture also brings that together. So in 1895, that's how long people have been thinking about this, a fictitious mean sun was introduced or was proposed to account for these fluctuations. In the length of a day. And so what this gives us is what's called mean solar time. So we're measuring with respect to a mean sun rather than with respect to the actual sun, saying, okay, well, on average, the period of Earth's rotation is this. On average, the time from noon to noon is this. We're going to be using that on average rather than the actual exact measured values. Okay, cool. So next, I want to move on to the next topic here, is universal time. And also something called leap seconds, which, yep, those exist. Okay. So first of all, mean solar time in Greenwich, England at the Greenwich Observatory is defined as universal time. So what's the significance of Greenwich, England? Why is that important? Anyone familiar with that place?
Sorry.
No, it serves as the center of the time zones.
Yep, it's right on the prime meridian. So when people were deciding all these things about like, okay, well, where is the global zero longitude point? The people in Greenwich, England said right here. And at that time, England was the most powerful country in the world. So everybody said, okay. And even now, when you hear Greenwich Mean Time, that's exactly this, mean solar time in Greenwich, England, Greenwich Mean Time, GMT, right? That's still something that we use today. Now, we must further correct for Earth's polar motion. So what we do then is we came up with coordinated universal time or UTC. Again, French backwards, is a correction of the International Atomic Time, TAI, by an integer number of leap seconds such that it matches universal time or Greenwich Mean Time to within 0.9 seconds. So basically, just coordinated universal time to account for the motion of the Earth. So leap seconds are added. There's a group of people, which we're not going to call the Time Lords, but that are basically Time Lords, that just monitor these things and determine whether or not we're all kind of still in some global alignment. Leap seconds are added at the end of June or December as needed. And I believe, if I'm not mistaken, that 27 have been added so far. So 20-second leap seconds since 1972. So UTC is the standard by which the world calibrates its clocks today. And because of that, I sometimes refer to it as internet time. You know, when you have a device that's been unplugged from the internet for a long time and then you plug it back into the internet and all of a sudden the clock is fixed, that's because it asked the internet, what time is it? And the internet runs on UTC. So once something is plugged into the internet, it is actually synced up to our kind of global time system. But otherwise, if you're just like running your phone on airplane mode for long enough, you'll notice that the clock will start to drift, the minute hands. Is that a hand up?
Yeah, I have a question.
Yeah,
Can
go
you
for
hear
it.
me?
Yeah, I hear you.
Have leap seconds been taken away, or can they be taken away?
I think they can. I'm not aware of them. That's a good question, right? Because one would think that if we're accounting for the Earth's motion, that every once in a while the Earth would like speed up or slow down. That's a good question. I don't know. I've only ever heard of them adding leap seconds. So could they be taken away? I believe so. It's a great question. This is something I would need to go do some more research on before I gave you a solid answer.
Gotcha.
But to my
Thank you.
knowledge, it's only been added. And now, those of you, maybe some of you have done some work before with something called SPICE. So users of the JPL SPICE ephemera system will be familiar with leap seconds. Because SPICE requires the user to have a leap second kernel. Or LSK, to determine the state of a planet, spacecraft, etc., at some particular time. And if you're not familiar with SPICE, you will be, because we're going to be doing that on homework 1. So basically, the folks at JPL have a solution to the math problem. It's a little bit like the Mayan calendar, where it's like we know exactly where Jupiter is going to be on Christmas Day 2060. We know exactly where it will be according to our kind of modern definitions of time and position and reference frames and so on and so forth. Somebody has sat down and worked that all out in a supercomputer and then basically saved the results in this massive database. And we'll talk about how to use SPICE, but you can use SPICE to look up the trajectory of spacecraft and the position of planets at different times. It's really cool. And we'll be using that a little bit on homework 1. Okay, so we are largely done with talking about time, although we've got one more time-related discussion. Let's get into the next thing here, which is reference systems and reference frames. So for better or for worse, there's going to be more pictures moving forward. For whatever reason, straight lines are a problem for me. There we go. So a reference system, as we mentioned before, consists of an origin and a set of basis directions. And those are typically mutually orthogonal. So x is perpendicular to y is perpendicular to z is perpendicular to x and y. That's our reference system and our basis directions. So a reference system is a set of instructions to form a reference frame. So the reference system is the recipe, the reference frame is the actual vectors. So what this does is it defines the origin and basis vectors, as well as algorithms to compute these. So then if a reference system is directions to form a reference frame, then a reference frame is a realization of a reference system. Okay. So it's time to learn about our first reference system, and that is the International Celestial Reference System. So this was developed by the International Astronautical Union. Or IAU. In this case, we have the letters in the right order. From 1997 to 2006. So we have the origin is at the Solar System Barycenter, or SSB. So you could think of this as the solar system center of mass. Isn't the solar system center of mass the center of the sun? Not quite. So the sun is almost all of the mass in the solar system, but you do have to take into account it's a weighted average of, okay, where is the center of mass of the sun? Where's the center of mass of the Earth and the moon and then all the other planets? And when you take their combined everything into account, then the solar system barycenter is very close to the center of the sun, but it's slightly different, and it moves, and it's moving all the time, which is really annoying, right? Because as the Earth orbits the sun, and as Jupiter orbits the sun, and all the other planets orbit the sun, each of their positions are moving, and then they're all moving at different speeds. The solar system barycenter is always moving, So immediately we run into an issue, which was, okay, well, where is the solar system barycenter right now, or where was it at some time? And we need to pick some epoch, some specific moment in time to lock it down and go, oh no, we meant its location then. But then why would we pick one time over any other time? They all seem perfectly useful. So you see the issues that we're running into here. We'll get into the time in a, and we'll see that those also vary with respect to time. So the axes, basis directions, are computed using directions to distant objects. So typically, extragalactic, so out of our galaxy, radio sources like quasars. So if we measure our basis vectors with respect to the planets all move. If we measure it with respect to the stars all move. Other galaxies also all move, but the further away something is, the less it appears to move. So we're going to use quasars as just about the furthest thing we could reasonably detect, reliably detect, I should say. We're going to work with those as our basis vectors, or as our kind of our distant datum points that we measure. Now, the z-axis is parallel to Earth's spin axis. Okay. So you could think of this as perpendicular to equatorial plane. The x-axis, this is where things get tricky. Do I have a picture of this? Or I think I draw one soon. Okay, so bear with me for now. The x-axis is the ascending node of the ecliptic plane on the equatorial plane. This is also referred to as the vernal equinox, or the first point of Aries. This is the weird one. This is the one that does not make intuitive sense to us. We think about it. What could possibly be the x direction in 3D space? Like, okay, the z direction is the Earth's spin axis. Sure, that's reasonable. Of course, that's always changing, but for now, that's reasonable. The x-axis is what? So I'll draw a picture in a minute, but basically, imagine the plane that the Earth orbits in, and then imagine the plane of the Earth's equator. Those are two different planes. Two planes intersect in a line, and we picked the spring direction as opposed to the fall direction along that line, because the Earth and the Sun are aligned at the vernal equinox, and then the diurnal equinox is when it is the Earth's orbit puts it on that exact line. It happens twice a year. We picked the spring one as the positive x direction. So I'll draw a picture of that in a little bit. But we'll contrary azimuth direction. And then the easy one is the y-axis. The y-axis just completes the right-handed system. Yes, raise hand.
Why is the z-axis chosen to be the spin axis rather than, like, I know like the solar system follows like a general disk of like of orbits. So like, why would we not choose like something more general to the solar system? Is that just by nature of like the missions we typically use? Like use this frame for? Okay.
Yeah, pretty much. Because most of our missions don't start at the sun, they start at the Earth. And so it's like working in the equatorial plane just makes things a little bit easier. But you're right. I mean, somebody could have easily chosen something else. Now, the Earth's orbit plane is not the same as any of the other planets' orbit planes. They're all slightly different, but they're all pretty similar. So you might say, why don't we take the average of all of the solar system orbit planes, and then that's our z direction? Yeah, I mean, that's a perfectly valid answer. This is just the one that the IAU picked. Yeah, that's a good point. And like I said, yeah, most of our missions are close to Earth, so we tend to like to use this. So
Thank you.
because, yeah, of course. And I'll draw a picture in a second because I know that the x-axis part especially is tricky. Because these planes or these directions are moving, you must choose a point in time or an epoch to realize this frame. So what we pick, we often choose the J2000 epoch, which, if you're going to pick something, the fact that we just had a new millennium within some people's lifetime, maybe not within your lifetime, but within my lifetime, the fact that we had a new millennium recently, that seems like a nice round number to start measuring. So that's what we did. So noon at Greenwich, England, on January 1st, 2000. Someone basically started a stopwatch right then, and the number of seconds since January 1st, 2000 is J2000 time. That's time since the J2000 epoch. So at that exact instant in time, someone said, okay, right now we pick the, we form the x-axis, the y-axis, the z-axis, and now, even a millisecond later, they're all technically slightly incorrect because all these different planes and directions are all moving. But we had to pick some particular time. We picked the J2000 epoch. So the International Celestial Reference System realized at the J2000 epoch is the International Celestial Reference Frame, or ICRF. We're going to be using that frame a lot in this class. Other times in literature, you might hear this referred to as the J2000 frame. Same thing. So the ICRF will be the world frame in this class. Or the basis for all other frames we use in this class. And then we will treat it as inertial. So somebody who, well, here, I'm going to start drawing a picture of the ICRF frame. This is something that Dr. Anderson talks about in his spaceflight mechanics class. What is an inertial frame, and why is it important that we have an inertial frame? Oh, okay, we can talk about that in a second. So let's say this is the sun. You got something?
Yeah, isn't it to satisfy like the like acceleration part of like certain ODEs when you're
Yeah.
trying to like analyze a dynamical system.
Yep, that's a pretty good way of thinking about it. So basically, Isaac Newton, there we go. So this is the equatorial plane. Plane, yep. And then this one up here is the ecliptic plane. So the plane of Earth's orbit and the plane of Earth's rotation intersect at a line. And then we take the positive version of that intersection as the x-axis. The y-axis is kind of arbitrary, and then the z-axis is along the Earth's spin axis. And so this gives us the ICRF. Yep. So Isaac Newton, when he figured out his, Newton's laws are valid in an inertial reference frame. So an inertial reference frame is two things: not rotating, so the basis vectors are not changing with respect to time, and not accelerating. So the origin point is also either static or it is moving with constant velocity. It's not speeding up or slowing down. This is not true of any reference frame. There is no such thing as an inertial reference frame, which means that Newton's equations are going to start to fail to describe the real physics of the system after a time, right? You'll hear me say this a bunch of times, but all models are wrong. Some models are useful. And Newton's equations are very good for a reasonable period of time. Now, if you've got something like the Earth, which is zipping around the sun, we can treat the Earth as an inertially fixed point. And that's fine for some time if you've got something that's orbiting the Earth. But over time, your equations are going to start to fail to describe the physics at play. Similarly, the center of the sun is also not inertial because it has its own motion with respect to the local star cluster and all that. Again, it's not quite inertial, but it's good enough for this class, so we're going to move on. We're going to call the ICRF frame the inertial frame. We're good to go for now. So sometimes a more local frame is useful for a particular application. So for example, why would we describe an Earth orbiting satellite in the ICRF frame? Doesn't make very much sense. I'd rather use a frame that's centered at the Earth, for example. So what we can do is the ICRF basis vectors moved to the center of the Earth forms the geocentric celestial reference frame. So geocentric, centered at the Earth, geocentric celestial reference frame. However, at least in my neck of the woods, this is more often called the Earth-centered inertial frame. Of course, that's a misnomer because it's not inertial, but close enough for our purposes. So ECI, you'll hear this referred to as ECI in this course. Now, the ICRF basis vectors moved to the center of the moon forms, if you could have guessed, the moon-centered inertial frame, or MCI. And so these frames are aligned with one another. So if you had a matrix, and we're getting ahead of ourselves here, but a matrix that describes the rotation from one frame to another, it would be the identity matrix, because it's the same frame, it's just translated, right? So you've got the sun's doing its thing, and then you've got the Earth orbiting the sun, and then you've got the moon orbiting the Earth, and this one has its frame, which is, but then this one has its frame, which is ECI, and then the moon has its frame, and I've tried my best to draw these in the same direction, which is MCI. So next, I want to talk about body fixed reference frames. So body fixed reference frames. Actually, before we get there, I'll make one more. I already talked about inertial frames, but I have a couple of notes on the subject, so we'll get there in a minute. And then we'll pause for questions. And we are in sight of the finish line here, so don't worry. We'll finish up at a reasonable time. So an inertial frame has non-rotating basis vectors. I've already said this. See that my notes are redundant. And a non-accelerating origin. Sometimes you'll hear this referred to as a Newtonian frame. None of these frames are truly inertial. But we can get away with treating them as such. Over short time spans. Then you might say, what is short? It's like, well, it's a little bit like when you linearize a function about a point. And it's like that linearization is valid close to that point. It's like, what do you mean by close? It's like, yeah, okay. It's kind of in the eye of the beholder. But the longer you let your clock go, the more Newton's equations aren't describing what's really going on here, basically. And so I want to highlight this, and I'll say this 1,000 times this class. All models are wrong. Some models are useful. Okay, next we'll talk about body fixed reference frames. Let's see. Also, I'll pause for questions. We all good? We're good on International Celestial Reference Frame, ECI, MCI? All right, moving on. Body fixed reference frames. Hang on, I get my notes all aligned. Okay. Okay, so we may want to use a frame with axes fixed in a planet's surface. Or a spacecraft body. or a scientific instrument? I feel like my handwriting started off bad, got slightly better as I got used to the drawing tablet, and is getting worse because my hand is tired. Sorry, everybody. We're on the last page of notes here, so we'll finish up soon. For a rigid body, the position of each point is constant with respect to time in a body fixed frame. So when we start talking about body frames and frame rotations, this might remind you a little bit of dynamics. And indeed, if anybody here has taken like one of the best classes on the subject at RPI is machine dynamics with Dr. Josh Hurst. If you've taken that class and you enjoyed it, then you're in great shape for this class. But if not, we're going to go over everything again. So hopefully it'll make sense either way. So let's talk about a frame at the center of the Earth. So consider a body fixed frame with its origin at the Earth center. So we'll make this part interactive. Somebody who wants to help me define an Earth-centered, Earth-fixed reference frame. Let's draw a picture. So anybody who's feeling bold, how would we describe an Earth-centered, Earth-fixed reference frame?
I feel like the obvious start is the center of the Earth as the initial point.
Yep.
And
which way is the
then
z-axis?
I'd go with the tilt of the Earth.
Okay,
It's like the free Pilates style. Is this all
this seems
vacation?
reasonable. There we go. So z-axis through the North Pole. And then what about the x-axis? This one's a little bit tricky.
Yeah. Are we trash?
Oh, I think someone might have a hot mic, or you're trying to answer and I don't understand what you're saying. But so let's think about it for a second. What seems reasonable to you, and you just being whoever feels like piping up, to define as the Earth's x-axis?
The prime meridian at the equator.
Yep, the prime meridian equator intersection point seems like a perfectly reasonable x-axis. Very good. So that is actually the 0 lat 0 long point, which I think is there's like a fun name for it. I can't remember right now. Point null, something like that. If anybody has like a crummy GPS that has ever just flipped out and said that you were in the middle of the ocean off the coast of Africa, that's actually 0 lat 0 long, which is a interesting problem that some GPSs have. So we're going to call it, say, x-axis through the intersection of the equator and the prime meridian, which is 0 degrees latitude, 0 degrees longitude. Great. And then the y-axis completes the right-handed system, which I'm too lazy to write that all out. So x cross y is z, right? Right-handed system. So this is the Earth-centered, Earth-fixed, or ECEF reference frame. Now, here's the fun part. I'm going to draw a picture. I already started drawing the picture. Let's say that at some moment in time, the Earth-centered inertial frame looks like this. Well, what you'll notice is the Earth-centered inertial frame has a z-axis along the Earth's spin axis, and so does the Earth-centered Earth fixed frame. They have the same z-axis. So at some future point in time, maybe I'll use red for this, you'll get a situation that looks like this, where we actually have the same vector in both frames. So this is the x direction in the ECI frame. This is the y direction in the ECI frame. This is the z direction in the ECI frame. But then over time, you'll get this z-axis rotation. So this is the x ECEF. This is the y ECEF. And this is the z ECEF. So there will be problems in this class where we say that 3 hours ago, the Earth-centered inertial frame and the Earth-centered Earth fixed frame were aligned. Now they're not. Okay, find the new Earth-centered Earth fixed frame with respect to the Earth-centered inertial frame. And we can do that. It's a z-axis rotation by some angle theta, and that theta is 3 hours worth of the Earth spinning. So we can do some fun math to get what that angle will be. And I'll walk you through that process later. But you can see how the relationship between the ECI frame and the ECEF frame is a simple z-axis rotation. All right. Now, you might be able to guess where we're going next. It's the moon. So now, consider a frame with origin at the moon center. All right. So in this case, we'll say that the z-axis is through the moon's spin axis, which for our class, we're going to say is close enough to the Earth's spin axis, that they spin along roughly the same axis. The x-axis is, again, is through the intersection of the equator and the prime meridian. Also, I think it's IAN. I think I misspelled it before. So that begs the question then, the moon has an equator and the moon has a prime meridian? Yes, it does. You could think of it this way. The prime meridian, so again, this is 0 degrees latitude, 0 degrees longitude. The moon also has latitude, longitude. This is the point that, on average, faces the Earth. So you ever notice when you look up at the moon, it looks basically the same every night except for the phase angle, right? So you've got like the same part of the Earth is always tidally, the moon is tidally locked such that we see the same part of it all the time. There is a little bit of kind of wobbling going on, but on average, we're looking at the same point in the middle of the moon, and that is the 0 degrees latitude, 0 degrees longitude point, if that makes sense. So it is the center as seen from Earth. Right, and then finally the y-axis completes a right-handed system. Right, and so you might have guessed, this is moon-centered, moon-fixed or MCMF frame. All right. We could also consider, and we're not going to go through a definition, but just could also consider a frame fixed in the principal axis of a spacecraft body. Or a frame fixed to an instrument, such as a camera. So you can imagine you've got a spacecraft, which again, I'm just going to draw as a cube. It's got its solar panels. And imagine that this particular spacecraft has some X direction, some Y direction, and some Z direction, or X, Y, Z, however you want to do it. Or imagine that you've got a camera, and I'm going to draw the camera. Ooh, I can do slightly better than that. Stand by. There we go. I'm going to draw the camera as a rectangular prism with a light baffle coming off of it. So imagine it's kind of looking out this way. It's got some direction here, and then maybe it's got some direction here and direction here. So you imagine you have a spacecraft body fixed frame or a camera frame, so on and so forth. So there's many, many frames we have to keep track of in this class. But the big ones that we're going to be talking about are the International Celestial Reference Frame, which is basically the sun frame. There's the Earth frame, and there's the Earth frame that spins and the Earth frame that doesn't spin. So Earth-centered inertial and Earth-centered Earth fixed. There's the moon frame. There's the moon frame that spins and the moon frame that doesn't spin. So moon-centered inertial, moon-centered, moon fixed. There's the spacecraft body frame, and then there's the camera frame. And those are the cast of characters that we're going to deal with in this class. And that's pretty good. That's an hour and a half. So I think, unless anybody has any questions that they think belong in the recording, then I will stop. In general, if you have content questions, we're going to ask those first so they make it into the recording. If you have questions like, what time are we starting lecture next week, or you didn't answer my email, kind of editorial type questions, then we will address those after we stop the recording, just because there's no point saving that. But yeah, so that was the first full-blown lecture in the class. Any questions about frames? All right, cool.
Yeah, I had
I'm going to.
Oh,
Oh, yeah. What's going on?
I had a quick one. Is
Yeah,
there
sure.
any instance where the x-axis of the moon-centered inertial frame lines up with the Earth one?
Let's see. The moon-centered inertial lines up with the Earth-centered inertial, or the moon-centered moon fixed?
The moon-centered moon fixed. Sorry.
Oh, yeah, they would line up at some point, right? So
Okay.
you figure every time the x-axis of the Earth is the Earth's prime meridian, and so that would be every time the moon is directly over the prime meridian, then you would have those two lined up. Now, not every time, because then there's like fluctuations in the moon's rotation and so on and so forth. But generally speaking, yeah, those frames will line up once per spin of the Earth on its axis. All right, cool. I hope my handwriting has been tolerable today. I'm gonna stop sharing and by no means kicking anybody out. We can stick around and chat for as long as we need to.